Howdy students, let's talk about the Doppler effect or Doppler shift. In order to do that, we have to talk about a way of representing a wave that we haven't so far, at least in this class, and that is in this way that you see here. So what we're identifying is this thing here as a source of oscillations of some sort. And for Doppler shift, it doesn't matter what kind. And so you've probably seen a wave phenomena that maybe looks something like this. And imagine the surface of water where this red dot is periodically poking the water vertically down onto the water surface and making ripples that propagate across the surface of the water. So what we're saying is that these waves are traveling. We're used to maybe drawing a wave like this and saying the wave goes that way, right? But waves probably don't, in many cases, they don't travel in a single dimension. They might travel in this case, 2 dimensions or even 3 dimensions if they travel through things like air or even in solids. So this way of representing a wave is called a wavefront representation. These things are all called wavefronts, each of these lines. And a wavefront represents a peak or a crest. All right, and a couple things you can notice from this. My diagram isn't awesome. It's odd because I really do make awesome diagrams. This distance from peak to peak, well, we know that as wavelength. Okay, and if you look anywhere around here, anywhere and everywhere, that wavelength is the same. If my diagram is as good as it's advertised. All right, so no matter where we go, wavelength is the same, and that's because in whatever medium this wave is traveling, the wave travels at a constant speed. And so in any direction, it covers the same distance in the same amount of time, and so there you go. All right. It's also we should make sure we say that this wave is traveling that way and traveling that way and traveling that way and traveling that way, and at any and every location, the direction of wave's propagation is perpendicular to the wavefront itself. I'm making perpendiculars. Now, I'm making that as a symbol. You might write that in words. That's called note-taking. So direction of propagation of wave is always perpendicular to a wavefront representation. Okay, so fair enough? Good. What you'll see in some cases, you'll see some wavefront representations where, what if we let these waves travel for really, really far, and maybe we couldn't even see the source, but these wavefronts are traveling toward us. We might see something like this, where we see parallel wavefronts that came from something way over here, and what we can't tell is they've spread out and spread out and spread out and spread out and spread out, and we're seeing a little tiny part of a much bigger wavefront. All right, so sometimes we'll see parallel lines that are straight to represent crests or peaks. Fair enough? Okay. Let's go here. Now, a couple things we can observe or point out when we use a wavefront representation, and that is that, well, there's a specific phenomenon that happens, well, really that happens everywhere in this area, because this is the area in which the two waves occupy the same space at the same time. And in that area, there are places like this, for example, there, and how about here, and sure, also there, and here, and at all those places we have crest and crest at the same place at the same time, and so those are locations of constructive interference. All right, it can be inferred that at every location that's halfway between two crests, there must be a trough. All right, so green line, dotted lines, I'm doing troughs. So at a place like this, Look at, there's a trough meets a peak. Here's a trough meets a peak. Here's a trough meets a peak. Here's a trough, a trough, a trough meets a peak. Those are all locations of destructive. Interference. Yeah, it's good. That's pretty much it for that one. Okay? So the nice thing is we can apply a different way of representing a wave to investigate or to show understanding of some wave phenomena. Now, Doppler shift by itself. So far we haven't talked about Doppler shift at all. But this representation of wave propagation is really the best way to get a sense for what Doppler shift is and how we can observe it. So, you know, imagine here's a source of a wave. For a Doppler shift, what you need are two things. You need something that makes a wave. So this thing is called a source of a wave. And what you need is a, he's around here somewhere. What you need is a, I'll find him. Oh, there he is. What you need is who is that? What is that? What is that little, you know that is? Look, that's me in my Einstein costume. So I'm not making waves, I'm an observer. Oh boy. This and that. Observer slash detector. All right, and so here's this source. In this case, we can, well, the source is stationary. All right, the source is emitting waves periodically that are traveling the same amount of distance in the same amount of time in every direction. So this wave is, or this source is stationary. And so if I'm here, oh boy, if I'm here, hey, no, stop it. If I'm here, those waves get to me every so often, right? If I'm here, those waves get to me every so often, right? Now traveling this way, all right? If I'm here, the waves get to me every so often as they travel this way, and so on and so on. So no matter where I am here, those waves will get to me every so often, the same every so often. And we call that the frequency with which I detect the waves. So no matter where I am here, the detected wave frequency will be the same thing. All right? But Doppler shift, come on, there you go. Thanks to the folks at ionkappa.org. This is some online repository of teaching materials. They have made this great app about the Doppler effect. And so what you do is you pop a plane here on this applet, and we can see the, let's call them sound waves, that this source emits, and that they travel at a constant speed in every direction. And so what we're trying to sort of show before is, you know, here's me, right? Here's me. Hello. And if we go back here and say wave source, let's look at how often I encounter waves, right? Right now. Sure. That sort of get a sense for that frequency, right? And then I go over here, and then let's see how often I encounter waves. Looks like now. Oh, we should also look at how often the source emits waves. Now. So the emitted frequency and detected frequency are the same thing. Maybe you're saying, well, of course they are, duh. Right? But watch this. Let's move this guy over here. Now watch this. What if, now what I can do is I can make the plane move. And let's try to count the detected frequency now. So boy, it looks like now. Right? Can you tell that's faster than before? Well, I should say is more frequent than before. So good. All right. So why is that happening? Well, look at this wave pattern. The deal is every one of these things is still a circle, right? This is a circle. And its center is like maybe here. And well, look at this one. This one's a big old circle. And its center looks like maybe here, right? And then, well, here's a tiny little circle. And its center is where the plane is right now. So what we can tell is this source, well, we know because we watched it happen, but this source is moving to the right, V source. And because of that, we get, you know, the speed of the wave, or the velocity of the wave, at least out in front of it, is to the right. And so this emitter of waves is catching up to the waves that it emits. At least those waves out in front of it. And so since it catches up to those waves, the detected frequency, the frequency with which those waves are detected by the person standing there, is higher than the actual emitted frequency. Wave frequency emitted by plane. Let me do this again. Watch waves emitted by plane. Ready? Now, 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 now. Watch waves detected. Now, 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 now. All right, so even though the plane isn't emitting waves at any frequency different than it did before, the frequency that they hit the observer seems higher, is higher. And that's called the Doppler shift. And what a Doppler shift is a difference in the frequency that a wave is emitted, or a difference between, I'll write it right here. Well, maybe write it right here, because that's the whole point, right? So a Doppler shift is a difference in frequencies, one, emitted by a source, and two, detected by an observer. There's a difference in those two frequencies. All right, we can see that. We'll do it again. Maybe I'm being redundant. I'll come right at him like this, right? Let's count emitted frequency. Now, 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 now. Let's count detected. Now, 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 now. That probably wasn't even fast enough. Okay? Now, what can also happen is let's let this plane keep, oh yeah, let's let this plane keep going. And watch what happens after, well, let's just do this. Let's do plane, hey, stop it. Let's do plane, yeah, let's let the plane do this. Look at detected frequency now. Bang, 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 bang. And that's a lot slower or less frequent than the frequency with which the waves are emitted from the plane. All right, again, plane emits waves at the same old frequency no matter what it's doing. It's a question of how often are those waves detected by an observer. And if there's a difference, we call that a Doppler shift. And there is a difference as long as, well, there's a couple ways we can have that happen. One way, oh boy, oh gosh, wait for it, there you go. One way is this. If we have a source, I mean, you should be able to, you need to be able to tell from this diagram that this source of sound is moving, or a source of wave, V source, it's moving to the right. And we can tell that again because the source is catching up to those waves out in front of it. And it's receding from those waves out behind it. So the velocity of these waves is, well, still perpendicular to the wavefronts. So the waves are moving in lots of directions in two dimensions, but the dimension we're really concerned about is this dimension. All right, so when we have this source coming at the observer, observer detects, and detects, right? The frequency with which these wavefronts hit observer is different now than it is now, even though the wave source moves at that same constant speed. All right, so what we would get, we can actually make like a graph. Oh boy. We could make a graph of frequency as a function of time, maybe. And what you would get is something that does, well, when we have source moving like this, that's a pretty constant frequency with which, or at which these waves are detected by observer. Ding, 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 right? And so that frequency maybe looks like this. I don't know. It's something. It's constant. And then, well, what we get is some instant at which this thing, or small range of times while this thing is passing, and then we get ding, 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 and that frequency gets a bunch smaller. So what we get is maybe something down here. And there's going to be some transition time there. Don't worry about that shape. All right. So the passing is occurring in that little amount of time. Yeah, fair enough. And this difference in frequency, this Doppler shift, I mean, the shift is really like from here to there. I don't know if that's what you quantify as the Doppler shift. The Doppler shift is probably how different the frequency is from the emitted frequency. And the emitted frequency is probably right down the middle, right? So here's F emitted. I think there's maybe only one M in emitted. And our red is F detected. All right, and so what we get is there's a detected frequency higher than the emitted frequency for some time, and there's a detected frequency lower than the emitted frequency for a time. All right, and if these are sound waves, we detect frequency as pitch. So you know what this sounds like? It sounds like, that's what it sounds like. We get high pitch, high pitch, high pitch, low pitch, low pitch, low pitch, low pitch, low pitch. But in the, you know, if this is whatever sound this, there's a person riding in the whatever making this sound, they don't hear the, whoops, they don't hear the, hey, come on. They don't hear the, they just hear, the person riding in the car doesn't. When you honk your horn and pass someone, you don't hear any difference in your horn. They hear it, you don't. Okay? So again, what we need is we need to have both an observer and a source. And the Doppler shift happens when, and only when, well, let me show you another case. Here's another way we can do it. Let's take this source, and look, we know from this diagram this source is not moving. We know that because it's not getting closer to any of the wavefronts in any direction. They're all equal distance from the source at any and every location and instant. All right, but there could still be a difference in detected frequency if, right, waves are moving this way in this dimension. Why? Moving this way in this dimension, that way over there, v wave, v wave. And watch, what if detector did this and then this? Now this is harder to see, but if we're doing this and going this way, v observer, right? When we're coming towards something that's coming at us, it seems like they're coming at us faster. Right? If we're moving at the waves that are coming at us, we will encounter them more often than we would if we weren't moving at all. Right? And then if we're over here and we're trying to catch up to those waves. Well, we won't be faster than the sound waves, that's for sure. The waves will catch up to us, but we're moving away from them as they're trying to catch up, so they won't catch up to us as often as they would if we were standing still. All right, so the bottom line here is a Doppler shift can be detected in one of two cases. Well, maybe I can make that in one cases, in one in one combined case. Only when there is relative motion between observer and source. All right. So if we had a case where source was moving to the right at that speed, but detector also moved to the right at the same speed, these waves would catch up to the observer because they move way faster than the source, probably. But if these two speeds were the same, we wouldn't get any shift in detected frequency. We have to have some difference in source speed and detector speed. Even if we did this, right, where source is or detector's moving but not that fast, right? Source will catch up to observer, and that means there's relative motion between them, and that means there will be a detected Doppler shift. And guess what? It won't be as big as it was in the graph we showed. Okay? Yeah, and the amount of the shift depends on how fast one thing moves relative to the other. Right? So if we go back to this thing, let me clean up this mess of circles and dots. So look, with slow speed, we get a pretty small difference in, a relatively small difference in the detected frequency when the object is approaching the detector and the frequency when the object has passed the detector. But there's a difference. Right? That difference you can detect visually by how close are the waves, right? I mean, if wave speed is the same everywhere, out here, you should add this to your, well, I'll just add it. Out here, what we get, this is a small wavelength. This is a large wavelength. Right? And because wave speed is the same everywhere, not source speed, wave speed depends on the medium through which the wave travels. These waves travel at the same speed in every direction. Well, when there's a big wavelength, there's a small frequency. When there's a little wavelength, there's a big frequency. Right? We're saying that v equals f lambda, and velocity of the wave is the same everywhere in that medium, so these are inversely related. Okay, so that means we can visually detect what's going to happen if we get this nice wavefront representation. We can see where wavelengths are small, we can see where wavelengths are big, and therefore we can tell the opposite happens to frequency. All right, so small speed, we get a small difference. Right, small difference in wavelength. Little wavelength, bigger, but okay, fine. A little, look, look at the top right, 0.4. The speed v of the plane is 4/10 the speed of sound. So let me get a difference that we can tell maybe a little more than before. Let's go to 0.5. Go to 0.5. Come on, there you go. And maybe we can tell a little more difference in how small the wavelengths are here and how big the wavelengths are there. Let's go to 0.6. Oh, we can definitely tell now. Look at that. Really tight up front, really spread out in the back. Let's go to 0.8. Crazy. I mean, the line's too fat to see the space between. That's, but they're really jammed up here and really spread out in the back. Let's go to don't do that. Let's go to 0.95. And it means, look, these waves will get a little bit farther, faster than the plane. See, they're passing the nose of the plane now. That means they're going faster than the plane, and we get a big spread out in the back. Well, watch this. We go faster than the speed of sound. And this wave, this source of waves, goes faster than the waves go themselves. And so what you get is, that's great. We get this cone thing here where there's, look at this, lots of wavefronts. This is part of circle, 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 all in this same line here. And that means that's just like waves occupying the same space, crests occupying the same space at the same time. Now they happen to come from the same source, but there's, a crest from this one and a crest from this one that occupy the same space at the same time. And that means that this line right here, let's go even faster. It means that that line right there is a place where there's lots of crests. And that means lots of constructive interference. And that means a wave with big amplitude. And for sound, that means loud. All right, so if I put observer back here, we'll put our little observer at, oh boy, we'll put our little, okay, fine. We'll put our little observer, hi, right here. Hello. Okay, very good. We'll try to do this right. Watch. Here goes plane screaming overhead, and look, the plane has passed us. Bye-bye, plane. We haven't heard it yet. A boom! And then we hear the plane pass us. Right? That is a sonic boom. Right? We can see the plane go past. We can, if we look straight up, we see the plane go, but the sound from the plane has not gotten to us until now. And then we hear it like crazy until it's passed, and then we just hear low pitch, lower than normal screaming jet engine sound. Okay? So, thank you to the Ion Kappa folks. Oh, sorry. And nice little app out there, demonstration of the Doppler Shift. And this gives you a good way to get squared away on what it's about. Okay? Here's what you gotta know for sure. The emitted frequency does not change. The frequency that the person emitting the source emits is constant regardless. The difference is in the detected frequency by something else that's standing around listening or watching. And guess what? This happens for light too, not just sound. It happens for any kind of wave, but it happens for light also. It's called red or blue shift. That's a topic for a different day. All right? All right. Fare thee well.